Okay, we're back for light waves. We spent a whole day on talking about sound waves. Now we're going to spend a whole day talking about light waves. And this is a great lead into our last topic on modern physics. Modern physics is based around some ideas that came out of studying light waves that were very, very surprising. So it's appropriate for us to spend a whole day talking about light waves. We're just going to do the basics today. Okay? So light waves, a fancier name for light waves, okay, and a whole bunch of other types of waves is the electromagnetic spectrum. And you see two words in there in electromagnetic that are important. Electro, meaning something to do with electricity, and magnetic, meaning magnets. Spectrum. Spectrum implies a range of something. Okay? The electromagnetic spectrum is the range of all the waves that are created by variances of electric and magnetic fields. Now, we did something about electric and magnetic fields pretty recently. Okay? We talked about electric and magnetic fields and how you can change one and change the other and all this other stuff. But one of the things we talked about with magnetic fields is how they can get created. One way to create a magnetic field is to take an electric charge that already produces an electric field around it and move it up and down, or just move it in general. That will create a magnetic field. Well, if you want to make a magnetic field that varies at a regular rate, what do? You take that charge and you shake it back and forth. Not only will this change the electric field at certain points, since you're moving a charge, it will also create a magnetic field that is varying. Okay? So these variances, therefore, light itself is created by accelerating charges. Taking charges and moving them back and forth, which has, in order to move them back and forth, you have to accelerate them at some point. Okay? And by charges, all we mean are protons and electrons. So if you want the really simple version of how do you make light, or how do you make any electromagnetic wave, take an electron, shake it back and forth. You are producing electromagnetic radiation, because that is what light is. Light is simply electric and magnetic fields that are kind of combined or related in a way. If you look at this picture carefully, you can see that they're actually perpendicular to one another, these fields. They point in perpendicular directions. That is what light is. It's a set of related electric and magnetic fields varying at a certain rate with a certain strength to them. Okay? Now this is really weird, because this means that all the light that you see, you watching this video right now, you looking around your room, you doing whatever, your eye is interpreting, your eye is essentially sensing a bunch of changing electric and magnetic fields, and it's turning that into pictures in your brain. Okay? It's taking those signals, and it's coming up with shapes of objects, it's coming up with colors, it's coming up with brightness. That is incredible, okay? That it's that complicated, that we are essentially seeing electric and magnetic fields. But our brain is telling us, oh, that's a color, that's a brightness. That is always crazy to me. Matter of fact, I remember, and you're going to have to ask me for the story, because I'm not repeating it on camera. My sophomore year of college, we were talking about this, and we were shown a movie about, I believe the scientist was James Clerk Maxwell. He's kind of the father of electricity and studies of electricity and magnetism. And he was the first one who determined that light is simply a correlated set of alternating electric and magnetic fields, okay? Changing electric and magnetic fields. And there was I wish I could find the video, because there's an animation that was really cool, and it showed in conjunction how both of them were changing at the same time. And, well, I'll have to tell you what happened later, but remind me to tell you that story. Okay. Anyways, electromagnetic spectrum is shown below. This is on your reference tables. I'll show you the same exact picture is on your reference tables. I'll show you right where it is. If you go to reference tables, here's the front. It's on the second page. Okay, we're looking at this right here. It says electromagnetic spectrum, wavelength in a vacuum up top. We've got an axis. We've got some bars showing different types of radiation. We've got a frequency axis on the bottom. Then we've even got this little section for just visible light. And I'll talk about what all that means. So you do have to practice reading this chart. Okay, it's not something that you can get away with not looking at before you go and take a quiz or a test or homework. You have to practice with reading it. Okay. Anyways, I'll scroll down so we can get everything on one page. Spectrum is shown below. Please notice that we can only see, out of all these, this is the only part of the spectrum we can see. Think about all the colors that you see as you look around. every single one of those colors is a type of light that fits in right here, this tiny little section. We can't see it, we can detect it, we can't see any of this, we can't see any of this. We can see the effects of it, but we can't actually see that radiation. So the visible light, the kind of light we can see, takes up a very, very small portion of the spectrum. It's like 1/100th of the entire spectrum, okay, of the spectrum that's like useful. Actually, no, it's even less than that. It's way less than that, okay? Please also notice that the frequency, that's the scale on the bottom, and the wavelength scales, please notice that they are not proportional. They are inversely related. Quick way to tell. Let's look at the frequencies first. We go from 10 to the 5th to 10 to the 21st. Frequency increases on this graph to the left. On the other hand, wavelength goes from 10 to the negative 13th up to 10 to the 4th. Wavelength increases this direction. Okay? So, what that means is that the bigger the frequency gets, as you go this way, the smaller the wavelength gets, and vice versa. And again, that makes sense because we remember this equation, V equals F lambda. For light in a vacuum, that's a constant, remember? We're going to talk about that in just a second. These two must be inversely related. So, the types of light, just to run down really quick. We've got, all four of these are all essentially bundled into radio waves, so all of these are kind of radio waves. We've also got microwaves, we've got infrared rays, we've got visible light, ultraviolet light, X-rays, gamma rays. Okay? And on the back, we're going to talk a little bit about each of those and what they're used for. But for right now, we're going to move on and talk specifically about the speed of light and something very important, one of the fundamental rules of the universe. And we talked about this before. In a vacuum just means empty space. Okay, if there's nothing in there, no air, no water, no dust particles, no other gases or anything, in truly empty space, light travels at a certain speed. And that speed is 3 times 10 to the 8th meters per second. That is on the front of your reference tables. And this speed has a special name. It's got its own variable or label. That is c. A lowercase c is the symbol for speed of light in a vacuum. The c, I think, is supposed to stand for constant. It doesn't change. Speed of light in a vacuum is always this. All right? Matter of fact, this is so important because this is the fastest that anything can go. This is the speed limit of the universe. There is nothing that can travel faster than this speed, 3 times 10 to the 8th. There is nothing that, no object can physically go faster than this. This is usually the part where people say, but what if? Okay? And I'm going to stop you right there. There is zero possibility of an object moving faster than this. Now, there are some ways, or there are some theoretical ways around it that no one has really tested yet. But you cannot take a baseball, let's do our tennis ball. We got a tennis ball right here. You cannot take a tennis ball and make it move this fast or faster than that. You can't even make it move this fast. Okay? Light is the only thing that can go this fast, and only in a vacuum. Anything with mass has to stay below that limit. There are a multitude of reasons why. Okay? You might think, well, what if I just keep giving energy to it, or I keep putting a force on it, cause it to accelerate past this? I'm telling you right now, experimentally it has been proven, the universe will not allow this. There are some changes that happen that we will not talk about in this class. You guys are in an intro class, okay? There are some things that happen with the speed of light that cause objects not to actually reach this speed. Some weird things start to happen. If you want to know more about that, go to the library. I'm happy to talk with you about it. But if you want to learn for yourself, go to the library, check out like an introductory book on relativity. Okay, A Brief History of Time might be good. Stephen Hawking. All right. Anyways, in empty space, this is the speed limit. No object can go faster than this. It's impossible for a physical object to reach that speed. The only thing that can go that fast is light, because light has no mass. It's a wave. Okay, at least for now, it's a wave. Hint, hint. Anyways, moving on. In other media, in other materials, light travels slower. For example, in water, light travels at only this speed, 2.25 times 10 to the 8th meters per second. We would not put c next to this because c is specifically just this number. When you change the frequency or the wavelength, that does not change the speed, okay? The speed is solely dependent on the material or the medium the light is traveling through, okay? So speed only depends on the medium. Now, here's what we're going to do. We're going to practice with this picture up here, with this scale, this graph, okay? I'm going to erase this. I'm going to ask some questions. We're going to go up to the graph and practice reading it. First question. Between infrared, visible light, and radio waves, which waves have the highest frequencies? So infrared, visible light, radio waves, which ones have the highest frequencies? We scroll up. Here's infrared. Visible light is right here. Radio waves are down here. Okay? Highest frequency, remember, frequency increases as we go to the left. Visible light has a higher frequency than all of those. So the answer here is visible light. Okay? That could be a Regents question. Something as simple as that. You need to be able to read, remember where that chart is, and then read it. So visible light has the highest frequency. Same question. Between infrared, visible light, and radio waves, almost the same question, which have the highest wavelength? Wavelength is this axis. Wavelength increases as you go to the right. So which one is farthest to the right? Okay, the frequency, we need the one farthest to the left. For biggest wavelength, you need the one farthest to the right. That would be radio waves. Okay, so radio waves have really big wavelengths. Visible light has very high frequency, at least of those three. And please do not tell me that radio waves are what comes out of your radio. Those are sound waves. The radio, your little radio that plays music and talk radio and everything, it receives radio waves and turns them into sound waves, okay? The radio waves are how the sounds get beamed across these big distances. The sound waves are what come out of the radio itself. All right, which has the higher frequency, violet or red light? We scroll up to our visible light section. Notice that all the visible lights are really close together, okay? It goes from 3.84 times 10 to the 14th for red up to 7.69 times 10 to the 14th for violet. So, which one's got a bigger wavelength, or bigger frequency, excuse me? That's got to be violet light. It's a higher number, okay? Quick hint when you're dealing with visible light, this chart does not tell you the wavelength of visible light. It tells you the frequency. So if you're ever asked what type of light a certain wavelength might be, or a certain frequency might be, or something that has to do with, like, you have to pick a color, and a color is involved in there somehow, please find the actual frequency. Don't try and guess based on the wavelength, because you will get it wrong. Actually find the frequency, and that'll make more sense when you actually do those questions. But what we need to do is you need to find the frequency there. So, which has a higher frequency? That would be violet light. And if violet light has a higher frequency, that also implies that it must have a lower or a smaller wavelength, right? So the next question down, which has the larger wavelength, violet or red? Let's see, so the first one, higher frequency. That would be violet light. Which has the larger wavelength? That would be red light. This is why in a rainbow the red is always on the outside, okay? The red is always up here, the violet's down here. It's because it has a larger wavelength, okay? I won't get into exactly why that correlates to rainbows, but that is the reason. Which types of waves would have wavelengths that are about the size of a human's height? You might be like, well, how the heck am I supposed to know a human's height? Think about a meter stick. It's about this much, right? Average person is between 1 and 2 meter sticks. So in scientific notation, that would be approximately, well, let's see. Is a person 10 meters tall? No. 100? No, we're going the wrong way. 10 to the 0, 1 meter tall? Yeah, possibly, about. For a really small person. Human height range is right about in here or so. Okay? We're definitely not less than like 1/10 of a meter. We're in here somewhere. So you're talking the very, very edge of microwaves, probably not even really microwaves. You're talking essentially radio waves, the waves that get beamed to your TV, FM radio. Those are all approximately on the order of a human height. Okay? So which type of waves would have wavelengths that are about the size of a human's height? Any of those that fit. Radio waves, FM, or TV. Okay? And those are all types of radio waves, but they're specifically saying FM and AM and TV just to give you a little bit clearer picture of what we're dealing with radio waves. It doesn't have to be just radios. Okay? I'll stop there. Go to the next video. Next video, we're just going to be doing really quick just some general facts about different types of light.